This video will serve as a demo for AI Fine-Tuning Circle. Welcome to the video series AI Explained Using Mathematics. In this first episode, we will demystify the concept of fine-tuning. We will specifically focus on vision models, adapting a general AI pre-trained model to master a specific case. Here, in our case, recognizing emotions in pet faces. But before we jump into fine-tuning, we need to understand the concept of learning in machines. For humans, learning means recognizing patterns in what we see, hear, or feel, and gradually making fewer mistakes. AI learns similarly, but instead of senses, it uses data. And learning happens by adjusting numerical weights to reduce errors. A model that has already learned patterns from some data is called a pre-trained model. Fine-tuning simply tweaks its weight so it specializes in a new task with less data. So, what exactly is the weight? At its simplest level, think of the concept output equals input times weight. Weight is a value controlling the influence any input data has. Let's look at an example. We have an input of 1.5 and we are trying to reach a target value of 9.0. For our first attempt, we initialize weight as 2.0 and multiplying the input gives a prediction of 3.0. Since our target is 9.0, our error is a bit large. We are 6 units away. So the network adjusts. Let's increase the weight to 2.9. Now 1.5 times 2.9 gives us 4.35. When we check the math, our error has dropped to 4.65. We haven't perfectly solved it yet, but by simply changing the weight, we have reduced the error and moved closer to the target. Furthermore, to determine if the model is learning properly, we visualize the error it makes as a curve. We plot the weight values on the x-axis and prediction error on the y-axis. Every possible weight gives an error on this graph, meaning the error changes when the weight changes. Our goal is to find the weight that produces the smallest error. To do so, we calculate the slope of the error curve with respect to the weight. The slope tells us which direction reduces error. If it's positive slope, we move left. If it's negative slope, we move right. The goal is to get a zero slope, meaning minimum error while learning. Think of it this way. To perform any task, we need an AI model. And for every new specific task, we could train a completely new model. But that means learning all the weights from scratch, which is slow and expensive. That's where fine-tuning comes in. Instead of starting over, we take a pre-trained model and slightly adjust its weight to fit the new task, mathematically nudging the model so the error curve goes to zero. And in this video, I want to show you two types of vision model that we will fine-tune, CNN and its ResNet version as well as the ViT. But first let's go into CNN, the Convolutional Neural Networks. But before diving into fine-tuning a CNN ResNet model for pet facial images, let's dive deep into the concept of input data, that is, in our case, a dog image. To a computer, a dog image isn't a picture. It's a grid of small squares, each represented by a numerical value called a pixel. Pixel has a brightness value between 0 and 255. Put all those numbers together and you get a matrix, with each square corresponding to a value. CNN uses a small matrix called filter represented by pink color here. They are also called weights that we discussed earlier. At each position, we multiply matching entries and add them to get the feature matrix that we are interested in. For example, in pet sentiment case, a mouth feature or a ear feature. Fine-tuning is simply the process of updating those pink numbers, weights, to detect slightly different patterns than they did originally. Visually, imagine pet face features, shape, texture, and edges mapped in a 3D space, where each sphere represents a feature. The weights act like invisible forces, pushing or pulling these spheres into specific positions. When we change the weights, the spheres shift to new coordinates, and that shift is called fine-tuning. That helps us distinguish between various features. The vision transformer. However, we need to determine how different parts of an image relate to each other. For any given patch, the model calculates an attention score. This is essentially a dot product between the vectors, a mathematical similarity check. By multiplying and summing these values, the network learns which features are relevant to each other, allowing it to focus on which patches actually matter. Once these features are extracted, they flow into the classification layer. Here, data passes through a dense web of hidden layers, condensing the information down to the final output nodes known as logits. Mathematically, every connection here represents a linear combination. The input is multiplied by a weight matrix with a bias added, generating the raw scores for our prediction of the picture. However, these raw logits need to be interpreted. We apply the softmax function to squash them into probability, in this case giving us 82% confidence that the image is happy. We then compare this prediction against the ground truth using a loss function. By taking the negative log of our predicted probability, we calculate a precise error value. This number is the feedback signal that tells the entire network exactly how to adjust its weights to improve next time, signaling the necessity for fine-tuning. With the exact error calculated, the real work begins. We feed this feedback into the fine-tuning process using the gradient, descent, or slope visualization that we talked about at the beginning. Mathematically, we adjust every single weight in the network by subtracting a tiny fraction of the error gradient. This slowly nudges the model towards accuracy. Visually, the effect of fine-tuning is profound. Before fine-tuning process, the model's data understanding is messy, with different categories overlapping. But as we repeat these weight updates, the network reorganizes its internal space. The data migrate and cluster, separating until a clear decision boundary emerges, giving us a model that can confidently distinguish the difference between our classes. In our upcoming circle on fine-tuning, we'll be going into it in detail. Make sure you have signed up for our platform and join the upcoming circle in advance. That's it for today. I hope you gained some insights into the mathematical reasoning behind fine-tuning by watching this video. Until next time, goodbye. Visit our website to learn more.